Welcome to the Saturday space stream of the Nexus Aurora Global Aerospace Innovation Network. I'm your host Koen from the Next Astro YouTube channel. This stream is now live hosted on our Nexus Aurora Discord server, to which you can find a link below the YouTube video. You can find many space-related projects on the Nexus Aurora server, which you can join for free if you want to contribute to space exploration yourself. Today, we will be discussing UV resin 3D printing in space. The Romanian student team of ECRIDA is creating a proof of concept 3D printer to prove the viability of UV resin 3D printing in space. It will be sent up on a rocket near the Arctic Circle in Sweden in March of 2022, which is about 462 days from now, as you can see on their website with that counter. All links to their website and social channels can be found below this video, as always. Today, I will talk to two of the founders of ECRIDA, Alexandru Hantașcu and Radu Șoca. And if there is one thing I hope that we can all learn from them, it is that with a lot of passion and hard work, even if you are a student, you can actually send things into space, which is great. So with that introduction, I would like to hand it over to team lead of ECRIDA, Radu Șoca.
Thank you very much for the introduction. Hello, everyone, and welcome to our discussion. First of all, I'd like to thank very much to the Nexus Aurora community for inviting us. And yeah, let's proceed with our presentation. We are the ECRIDA project, and we are going to present our experiment and talk to you some things about 3D printing using UV resin, and also how we want to bring this concept to space. Regarding our table of contents, we are going to talk about who are we, about the REXUS BEXUS program, which is the program that we are currently involved, and we are going to give you some thoughts about microgravity research, and then we'll dive right into our experiment. And what are we planning to do with it, and in the end you will hear from us some details about the future as we see it about manufacturing in space. And in the end we are ready to take some of your questions in order to answer them. So let's dive into it. My name is Radu. I have a bachelor degree in electrical engineering, specialized in control systems, and I'm currently a master student at the University Polytechnic of Bucharest. I currently also work as a satellite guidance, navigation, and control engineer, and in my free time, I am the team leader of the ECRIDA project and also one of the responsible for the electrical design of the project. I'm also interested in system engineering, space project management, and I'm quite often looking into rocket and balloon science. Next, I will give a short introduction to my colleague Alex, which you'll meet soon. He's a mechanical engineering student, also at University Polytechnic of Bucharest, and he's also the mechanical responsible of the ECRIDA project. He's a guy very passionate about 3D printing, additive manufacturing in general, and he's looking forward to find more things about space and manufacturing technologies. Going next, about the REXUS BEXUS program, those are basically two acronyms for rocket and balloon experiments for university students. It is basically a program organized as an agreement between the Swedish National Space Agency, the German Space Agency, and also the European Space Agency. They together offer the possibility to allow students from Europe to launch their experiments inside rockets in a suborbital flight or inside stratospheric balloons and inside stratospheric balloons, yeah, that will be over here. Going next about the REXUS part. Each year, the organizers send in the flight 2 rockets, and each rocket holds four teams. The teams are basically responsible for the whole design of the experiment, its integration, and also the science part of the experiment. To give you a better insight, the teams have to implement their experiment inside a cylinder like the one you see here. Basically, each cylinder that you see in one of these pictures, they go to a university, the students assemble the experiment inside it, and at the end they send them back to the launch site. They mount all of them together, and they attach in the end the motor on the bottom of the payload, and that's the whole REXUS rocket. On the BEXUS part, the BEXUS part launches a balloon each year, holding 8 student experiments. They are also responsible for everything regarding integration and science. And basically, they get here a stratospheric flight, like about of 1 or 2 hours, it depends, and they experience conditions like low pressure, solar radiation, other types of radiation at high altitudes, and other types of harsh condition for their experiments. To go next, I'm going to talk about microgravity research. Why microgravity research? As our team, it's part of the REXUS program, which is inside the rocket. The rocket will experience a short period of low gravity, and usually most of the experiments that are hosted inside the rocket, they have to take advantage of that period, basically do microgravity science and researching something related to this phenomenon. So microgravity research.
Seems that we have lost Radu for a moment. We're waiting for him to reconnect from Romania. Alex, is there a possibility that you could try to find a way to open the PowerPoint yourself and share your screen if Radu cannot reconnect?
Yeah, I think, yeah.
Radu is back again, so let's try this one more time. Radu, can you share your screen again so we can continue the presentation?
No, can you hear me?
Yes, we can. Thanks for reconnecting. That's great. We can hear you just fine. Thank you.
So just give me a feedback if you can see the screen.
Yes, we can. So
Okay.
it's looking and sounding great again.
Yeah.
You can continue the presentation. It will be fine.
Yeah, thank you very much. I was talking about microgravity research and the fact that our experiment will be exposed to a short period of reduced gravity. What is the purpose of microgravity research? Basically, we want to see how gravity impacts a specific phenomenon. Usually, when you want to see the impact of, let's say, temperature on a phenomenon or something, you are able to do experiments like change the temperature, reduce it, or things like this. But when we talk about gravity, we, as always, made assumptions, but we have to do experiments to see if we are right and if the main reason for something is really the gravity. This is quite an emerging field right now, and it's quite improving. There were some advancements that show that new manufacturing possibilities can show up while they are performed in microgravity, and they give better results. And there are some others, biological and even drug development that can get us better results if they are performed in microgravity. And the question I'm going to answer next is basically how can we get microgravity? And this is quite a challenging question because it's quite difficult to remove gravity from the equation, but we can somehow fake it, and there are some ways, some cheaper ways and some more expensive ways. It depends on our requirements and the time of reduced gravity that we want. Of course, the first method is to do our experiments inside the International Space Station or during an orbital flight, maybe on board another spacecraft that orbits the Earth or another body. Going next, another method which is quite used these days, it's the use of parabolic flights. How this works, there's a regular plane that performs parabolic trajectory, and the people inside it experience periods of low gravity and high gravity, depending on each part of the parabola they are. Next, another method which gives quite a short time of microgravity, but for some experiments it might be useful. Are the drop towers. Basically, you mount your experiment inside a capsule and it free falls inside this tower that basically also have all the air removed. It's a vacuum. They try to fake a vacuum inside it. An example is that the Tsar Bremen drop tower from Bremen, Germany, which is managed by the Tsar Center, and they are also a partner of the REXUS project. And another method to get reduced gravity is, of course, flying your experiment inside a rocket in a suborbital flight. Suborbital means that the end of the trajectory is always back on Earth, so you don't remain in an orbital flight. So it looks basically like this, like the image you see on the left. You launch your rocket, you experience at the apogee a period of reduced gravity, and then you fall back, hopefully in a controlled manner, and you land safely using a parachute or something else, and then you recover your payload in order to get back your results. This procedure also happens in our case inside the REXUS rocket that you can see here on the left. It is a rocket that is launched, as I said, every year from the northern Sweden in the Arctic Circle, close to the Kiruna town in Sweden. And now next, regarding our project, yes. So as I said, our project is part of the REXUS BEXUS program, and we have basically two objectives: to prove the viability of DLP 3D printing for materials processing. DLP is a method of UV resin printing, a method that I am going to explain in the next slide. And also, we want to determine the physical and mechanical properties of our samples. We have some scientific assumptions that the samples that will be printed in reduced gravity will have better mechanical properties than the ones printed on Earth. About UV resin 3D printing, maybe some of you are already familiar with this because this method of 3D printing became very familiar in the recent years. How it works, you use a resin that is basically photosensitive. When you expose it to UV light, it solidifies, and like this, using, let's say, a laser, a screen, or maybe other ways to expose the resin to light, to UV light, you can print different shapes on a build plate that moves up and down. And you basically print it layer by layer by exposing each layer to a shape of light, let's say, of UV light. And this is basically what we are trying to do in microgravity. Of course, there are some challenges that you already might be aware of. The first problem comes from the fact that you have to handle a liquid in low gravity, and also you have moving parts, and you have to take care about temperature and all other disturbances that happen during the flight. So about our project, how it works, and you will see that it's very simple. It basically it is mounted inside the REXUS module, and I will explain step by step. Let's say how it works. It on the top it has a stepper motor together with a lead screw mechanism that moves this plate up and down. This plate is immersed in resin, and on the bottom we have a UV light source that passes through a mask, and that mask give a shape for the light and for the samples that will be printed. We print one layer, and then using the motor we lift the bit plate up, and then we light again the UV light and print the second layer. We are going to print 10 layers, and we are going to get 24 samples in the end. Another point to mention here is that this box is pressurized, so is a pressure vessel in order to keep the liquid contained and not have any problems with it. What I presented earlier, it's briefly presented here in this animation, so you can better understand. So the build plate moves up and down, there's a backlight, there's a mask, and the light goes through this mask and prints layer on the bottom of the plate. And we are going to print 10 layers, and the overall height will be 1 millimeter of the layer. Going next, this is how our samples look like with some tests done on Earth. On the right, you can see the mask that I was talking about and the shape forms. And on the left, you can see the samples. Why the samples look like this? They follow a specific standard that can be easily analyzed after the flight. Basically, we are going to also have some destructive way to analyze the samples. We are going to break some of them in order to find out some properties. Our experiment at this moment, it is in the integration part after, let's say, almost 2 years of continuous work. So we are in the stage where we have to manufacture the final product and deliver it to the agency that will assemble the rocket and invite us to the launch campaign. So here you can see how the experiment will look like in the end. That's a CAD model generated. And here there are some parts that have been already manufactured, and we are going to perform tests on them. Next, you can see here a 3D printed version of our, this is how it will look in the end. Those are 3D printed from plastic. We use this model to test some assumptions and to do some tests. And we also have an electronic box attached to it that controls everything and also holds the sensors of the experiment. So yeah, this is our team. We are really 10 members in the team. You can see here our module, the blue one, that will host our experiment, and it will be on top of it. We will have another experiment, and on the bottom, of course, another one from other 2 universities. And yeah, this is our team right after we received the module, and this is also a 3D model printed that was placed inside it just to see if it fits well. Regarding our schedule and what we are basically doing next inside this campaign, we've been subject to different reviews held at different space agencies' headquarters. And next, in November next year, we will have the Experiment Acceptance Review, EAR, that will give us the certificate from the organizers to mount the experiment in the rocket. Basically, this will come after a series of tests like vibration tests, shock tests, vacuum, thermal tests that will be performed in the next period. Then we'll have some weeks where we are going to test our experiment together with all the others' experiment in order to see how their experiments influences our own in terms of, let's say, communication, power consumption, mass, and maybe other interference. And in the end, in March 2022, we will launch our rocket from Kiruna at the SSC, Swedish Space Company site. It's called the S-Range site in northern Sweden. These are some pictures with our team. We spent quite a lot of time doing presentations like this, traveling to when it was possible, yes, before the crisis, to give presentations and to defend our design in front of the panel. And yeah, we are also spend a lot of time in our laboratory at the University Polytechnic of Bucharest, where we basically do things like vacuum testing, performing integration, unitary tests on the subsystems, and everything related to the science of the experiment, the resin, its properties, and all the analysis. And next, I would like to invite Alex to continue the presentation. So Alex, if you can unmute yourself. You can
Yeah, thank you, Radu. I think I hope that you can see and hear me well. So now I'll present you some interesting developments in the additive manufacturing and how we see the future of 3D printing and how in-space manufacturing objects can have huge benefit in the space industry and other industry also. So well-known application of the microgravity manufacturing is the possibility to manufacture different materials and drugs in space. So in the left pictures, we have some examples of fiber optics. So the messy one is a fiber optic considered a good quality on Earth. And the clear one, it's a fiber optic manufactured in space. The photo is from a company named Made in Space. And what they found is that fiber optic made in space is more dimensionally stable and also better quality than any fiber made on Earth. And also the other three photos shown very well the way microgravity influences the flow of liquid. So the photo is from another REXUS BEXUS student project that's called AMIS. They develop an extrusion process of a UV resin. So they are using actually a resin, the same resin as we are using. And they try to analyze how gravity influences the extrusion process. So you can see in the second photo, the extrusion process is done in 0G. And the extrusion is very constant, so it's very dimensionally accurate. And the other two photos are made in Earth condition, so with 1G gravity. And you can see the extrusion shape, it's different and more difficult to compensate in a manufacturing process. And now let's imagine that we have a reliable manufacturing method like 3D printing, extruding, or other manufacturing method optimized for a low gravity use. We are not limited by a small number of materials. For example, a resin can be used also with other additives, so we can mix it, ceramics, metal powders, magnetic powders. And for example, by using a 3D printing method, magnets with 3D printed magnets can be made with a specific field. So like the ones in the left top photo, or a little magnetic robot can move, fold, or carry payloads to a specific location. Of course, they can move in a magnetic field generated by an external source. So there is still a dependent on an external source to move or fold. But the process of obtaining this type of magnets or robots, it's not very complicated one. So the resin is mixed with the desired additive, like in the last picture, and printed using UV light. The material can be extruded or 3D printing using other methods. Now, another important thing is the power source. So in a conventional way, in an environment far from Earth, the main source of power would be the sun. So by using solar powers to create energy and use that energy for different machine and tools. So in our mind, an idea come, and why to have so many steps converting the solar energy to electricity. So we also thought about a more efficient method. So why not use directly the solar power for a manufacturing method? So our idea in the future is to change our exposure method. So in our experiment, now we are using a LED-based method. So we are generating the UV light using LEDs. So we want to convert that to a sun-based one, because the majority of the energy necessary for the printing process, it's used by the exposure method. So that would mean a more energy efficient printing method. Also, another advantage is that on other planets, for example, the solar radiation is more powerful. So on Mars, it's 100 times more powerful, and on the Moon, it's 200 times more powerful. So on Earth, some manufacturing methods mainly based on solar power were tested. For example, this is a printer made by an artist that it's using sunlight to melt sand in different shapes. And lastly, I'll present you another student project that it's also participating in the REXUS BEXUS project. The project, it's named MASS, so it's manufacturing of structures in space. So they aim to study how to manufacture structures in space, and also the main energy source of the experiment, it's based on sunlight. So they made an origami folded shape, as you can see in the left lower photo. So the material of the origami shape, it's a resin impregnated fabric. So they inflate that origami shape and let the sun carry it. So in the right photo, you can see how they inflate it. They let it inflated, the sun cars the resin, and after the carrying process, the structure remains solid. So that's how solid the shapes can be manufactured rapidly, and also how we see the development of this printing method in a space application or other industry. And now, those are our sponsors and partners. We thank them very much for their support, because they gave us some support, and they've been there in our journey to Kiruna. And thank you also for your attention.
Yes, and thank you guys for this interesting presentation. We see a lot of sponsors here that made this journey in 2022 or towards 2022 possible, of course. And it's very interesting to see a team of students actually carrying out an actual real life experiment. So already, even though it still needs to start and happen, congratulations on getting accepted to launch on this rocket, of course. So there are a lot of questions that people have been asking us, and I'm just going to go through them, and I hope that you both would be willing to answer them, and you both can decide which of you answers the question. So one of the questions is asked in the space subreddit, where we posted about this video, this live stream, of course, and that is, so how do you even prepare for a test of 3D printing in microgravity? What can be done while here on Earth to test such a thing? Or is it all just really hoping that it will go right? Because you only have one chance, right?
Yeah, I will take this one, I think. Basically, as you said, first of all, testing in microgravity, it's quite expensive, first of all. And yeah, the first test will be this one. And if results show us what we expect, that we find better results in microgravity, then we plan to go into as I presented, there are other ways to get microgravity. We are mainly thinking about the parabolic flight that will go next. There's also a program called Fly Your Thesis, organized by European Space Agency, and they allow students to perform parabolic flights with their experiments. So that will be the next step for us.
Yeah, that sounds really, really awesome. I hope you guys can join in the parabolic flight yourself, because that's, of course, very important. That would be awesome. So you can become weightless yourself at least a number of times for a short period. So there's one thing that's actually interesting that last summer I actually drove by this very launch complex when driving through northern Sweden and Norway, but I just didn't know it was there. I should have known this. I should have known you guys before this, but there you go. So you guys talked about during this presentation that you started a project that you have been working on this specific experiment 2 years ago. But is that actually the real first time that you started working on the project, or did you start even before that?
Um,
Did,
let's
did
say, are you asking if we knew each other? Okay. Basically, yes, we knew each other from other, but let's say not really space-related projects, also inside the university. And yeah, we first did that I have to mention. We begin with the idea to do something in the space domain for the REXUS, and then we came up with the idea of 3D printing there.
Okay, yeah, that's clear. So yeah, that's at the University of Polytechnica Bucharest, right? All of you guys are there. Yeah, that's great. So can you tell our viewers how many seconds of microgravity you are going to expect? Because there are also some questions about if this rocket is going to get in orbit. I think I can answer that. The answer is no, of course. But how many seconds of microgravity do you expect, and how many layers can you print during that time?
Okay. I can also take this one. So yes, the rocket will not go into orbit. It requires a way bigger motor and way bigger velocity in order to do so, and it isn't its purpose. But mention here is that suborbital rockets, they sometimes they basically can reach higher altitudes than orbital flights. So somehow it's not really, let's say, a worse vehicle. It depends on what you want. Yeah. So basically, yeah, the purpose is not to have orbital speed here. And regarding the period, it depends also, because it depends on the mass. Each team have different masses, and yet we don't know what was the mass of each experiment. Even the motor, it's not quite. We don't know yet the exact mass, but we expect around 120 seconds of milligravity. But another mention here is that we don't have the same gravity during this period. Usually at the apogee, it's the finest time to print and the lowest period, yes. And about the layers, of course, the layers are in relation with the time that we have. We usually found out that we can print one layer in only 6 seconds of curing. So we aim to print 10 at the moment, 10 layers of resin during this period.
Yes, because in your presentation you showcased the test materials that you're going to test afterwards for strength. And the nice thing about UV printing is that you can do a large area at the same time. So can you talk a little bit about the final thickness of the material that you're going to print in these 10 layers? Because in, let's say, resin printer that I could buy on the market, that would be a very thin thing, but I guess you're going to do something clever and make it a bit stronger and thicker, right?
Yeah, I let Alex to.
Yeah, you can hear me? Yeah, okay. So what we're printing are some traction probes. So they have a specific standard. The standard that we are using, the thickness of the probes are 1 millimeter. So we are just printing 1 millimeter thick probes. So every layer it's 0.1 millimeter thick. So we are using 6 seconds for a 0.1 millimeter layer.
Yeah, that sounds about right. Yeah, I'm really interested to see what the results will be, of course. So Sean from our Discord server actually asks what quality you expect from the prints compared to, for example, the same experiment done on Earth.
Okay, Alex, you can.
Okay, so as we said in the presentation, there were some experiments that investigated how different materials develop differently in low G environment. So we think that the mechanical properties of the probes will be superior on the probes that are printed in space, and also the way that the probes solidifies. So the way that the rising cures will be different. So the way all the atoms will take shape will be more organized.
And with more organized, you mean that the bonds will likely be stronger, and you expect to see that result from the 3D printing in space, right? Because the interesting thing is that before I listened to your talk, my idea would be that the reason that you do these 3D experiments would mainly be for a future where 3D printing in micro or zero gravity would be essential for our survival in space. I don't know if that is your first thought, this was your idea behind the project, or was the idea more like, hey, printing in space can give you higher quality than on Earth, like with the fiber optic cables, as you mentioned? What was the original idea behind it?
So the original idea wasn't just to develop a material that it's stronger just because it's 3D printed in space, because that also would mean some additional costs. So it's expensive to print something in space and bring them to Earth. Like that's why we don't have for now fiber optics printed in space and bring them to Earth, because it's very expensive. So we also thought about using them in space, like a more space-saving solution. So you actually have a liquid that you can carry on with you, so you can maximize the volume of your spacecraft. So you can put you don't need to bring with you tools or other equipment. You can just 3D print it and use the liquid that will fit in a more space-saving way.
Yes, that sounds very logical, and that seems like a good idea, at least for the future, where spaceships like Starship will be flying and making access to space a bit easier and cheaper. One competitor of this Starship by SpaceX is Blue Origin, and we have a question here, and that is about Blue Origin's New Shepard suborbital rocket. Would this be a potential test rocket for you guys? And would that be better or worse than your current method?
I can answer this one. So it depends on how, because of course it will experience a lot of reduced gravity. But let's say that in the future, yes, it is a viable way to get reduced gravity, but we have to see exactly how much time it gives. But yet I want to mention there are a lot of new vehicles coming. We heard about some rockets that are reusable. They basically land back. and they can redo. There are some people from Australia. We will share the links with you. That they can do like 5 or 6 launches in a day with that, and basically achieve the same period of reduced gravity. But the period of gravity is not the only things that matter. It's only about the payload mass, because they can only have like a payload of a few kilograms. And as an example, our 10 kilograms right now. So it depends. But the answer is yes.
And would there also be possibilities to scale down your experiment in mass as well? Would that help get you more easy access to those kinds of experiment? Or is this like the limit that you can bring it to, you think?
Basically, the development that we also presented, it was using solar radiation as a power source. So this will mean we will, in a case of developing something like this, you can remove most of the electronics that will drive it. And yeah, we think the mass can be reduced. Yes, but also in our case, we have to make sure that everything is pressurized. So yeah, we have to have like thicker walls and to have a strong structure.
Yes.
Yeah.
So as you showed, you created a 3D CNC milled metal enclosure to create this enclosure. Yeah. That's still probably going to weigh a lot.
Yeah.
Add to the mass, of course. So we get a question on the space subreddit by Electron2302, and he asks about the DLR, the Deutsche Luft- und Raumfahrt. He sees that as a logo. Can you tell us about your connection to this? Or what your collaboration is with them?
Yeah. So basically, the REXUS BEXUS, it's organized as a bilateral agreement between the SNSA, Swedish National Space Agency, and DLR, as you said. They together offer the possibility for students to join it. ESA came as an interface on the Swedish part that shares its share with all the countries from the European Space Agency. So DLR, and together with Sam from Bremen, and together with Moraba, which is a department inside DLR, they basically offer the technical support and even some subsystems of the rocket, of the REXUS rocket.
Yeah, that's awesome. A nice, typical, you could say, European project with a lot of different countries involved. And well, what is really awesome is that you guys, as students, get a chance, of course, to participate, to learn a lot, and actually send up your stuff without needing to be rich yourself to do this. So really cool that you guys have been working so hard on this, for sure. And sharing your knowledge here as well. Really great. So another question on the space subreddit by Pawnstar is Pawn, I should say, is that he first of all wants to say that he's really interested and wants to see the results. So he's going to keep following you guys for sure. And he has a question about how his 3D printer with which has a nozzle, so I guess it's an extrusion 3D printer. It doesn't seem to have anything to do with gravity on how well it prints. So it's not really a question, but maybe I can make it one. Would it be if you would use an extrusion 3D printer in your experiment as well? Would this give you very different results? Would this even work? And have you considered using extrusion as a possibility or not?
Yeah, I think I can answer to this question. So we also talked about other techniques, so extrusion-based, FDM-based. Actually, at the first stage of the project, we also talked about using thermoplastic instead of resin. But we thought about some key aspects. So firstly, yeah, it's also okay to do an extrusion base also with thermoplastics or other materials, but there are also some limitations about the resolution and the detail that you can obtain, and also what parts you can make That's why we thought about using resin printing, so using like a DLP1, because it's faster. You have greater accuracy. You can also use more materials. So you can have ceramic resin that you can print anywhere and cure them after that, or you can have a magnetic resin. Those kind of applications are quite tricky when you're trying to use an extrusion system, and that's why we thought about the resin one.
So a question by me this time, because of your answer. I would say that there's at least one other option that you could use, and that is maybe a laser metal sintering, right? That's another method of creating like a metal bond in space, which seems to me would be very useful in space applications, specifically to create new pressure vessels, for example, to live in maybe in the far future. Has this been considered as well, and why did you choose to go for resin instead?
So actually, another Romanian team that participated in the REXUS program studied how to weld different materials in space using a laser. So yeah, it's also a good alternative, but the disadvantages are that you need also a more special environment that using resin. So using resin, you need also less power to make an object, but using laser, if you're trying to make something from metal, you need a powerful laser. You need a special container, because when you're melting that metal, there are other elements that appear when the melting happens, and also you need to clean the part. So you have a lot of powder that you actually don't want to clear it in the ISS, for example, because that very little powder can go into other electronic stuff or at the personnel in the ISS and can be harmful. So but if you're trying to make something on another planet, or make some bigger structures based on a laser or something, it may be reliable, but the environment needs to be very well controlled, because as you know, maybe there are some problems with the metal sintering for now, because there are some voids that appear in the part because of the melting, and also the printing chamber needs to be filled with argon or other gases, because to sustain the printing process.
Yes, these are all good points. But actually, the contamination of, in this case, the ISS, where you could do this, I never thought about that. So a great thing that I learned from you. That's great. You also showed in your presentation a way to use a lens to create some type of 3D printing, even though it's maybe low quality and not very precise yet, but to a kernel lens, I think, or Fernal lens, something like that, and that creates like a concentrated solar area. And that could be used maybe on other planets or on the moon or on Mars to create like maybe a bit of a relatively low tech and lower quality 3D print. I know it's not your project, but could you tell us a little bit more about that, because it looked really cool as well?
Yeah, sure. So actually, I don't know if the presentation is still on, but if Radu can go on that slide. So
Sure.
actually, the device that you've seen in the presentation, it was made by an artist, as I know. So yeah, it's actually using some kernel lens, and what it's doing is something similar to direct metal 3D printing. So it's using sand as the base material, and the sun it's focused on a specific spot, and it's just moving the plate in a planar plane to make the 3D object. I don't know very much about the mechanics and how it was developed, but yeah, as you said, it could be a reliable way of making big structures, not very accurate, but big structures in a different environment.
Yes, and thinking about Mars, I think maybe the moon with a lower atmosphere would be a better place to do this type of work, maybe. But I just thought it was a really cool thing that you added to your presentation. Talking about lower gravity environments instead of zero G or micro G, as you are going to work in. Um, do you know anything, or can you share anything about, for example, resin printing on 1/3 the gravity, like the moon or Mars? Would that change the properties as well, do you think, or would that be very similar to Earth because there's still a decent amount of gravity?
So I don't think I can say exactly that will happen something or not, but based on our knowledge and what we've tested, when there's a low gravity, also the printing process happens differently. I'm not very sure if the printing process will result in better quality prints on moon, because there is still some gravity, but I think it will simplify some part of the printing process, because you still have gravity, so your liquid will not float around in different places. That
Well, Alex is gone, so he's gonna be back. Okay. It was a clear answer already, Alex. So I'm going to ask the next question, because we're almost already, I think, streaming for an hour. So I'm going to have to pick and choose the few last questions that we have. And I would also like to say that all the people watching this can actually join the Nexus Aurora Discord server and have a discussion that continues after this live stream on our Discord server, where we are actually streaming this from, as you can see. So Alex and Radu are going to be there right after this stream ends, and you can still ask them as questions as well as all the people who are a member of Nexus Aurora, which is free to join, will also do. So the last few questions, if you don't mind, are two things, and one of them is if you have any information about 3D printing application in medical sciences, and if those kinds of medical sciences are interested in the results of your research. Can you tell us something about that?
From what I know, maybe Alex can add more. There are results showing that some proteins or biological compounds act different while they are, let's say, the drugs are manufactured in low gravity, and there are some research ongoing on this. But also regarding the second part of the question, we are currently not collaborating with anyone from the medical side. Yeah. So yeah. So, yeah.
Yeah, that's very interesting. So, as a final question before we close off the live stream and continue on the Discord server, so could you tell us what the biggest hurdles were that your team has gone through and still need to go through before you achieve your own objectives with this project? Because in 2022 you're going to launch, of course. Maybe tell us something about the way forward towards 2022, and maybe even after, if the project keeps on going after that. Thank you so much.
Thanks for the question. Basically, it was not mentioned, but initially the launch was supposed to take place in 2021, but it was delayed caused by the COVID crisis. So it was delayed entirely with 1 year. So right now, as I presented, we almost have everything ready in terms of parts that we have to assemble and perform some tests. There will be vacuum tests, thermal tests, vibration tests that will be will be performed by us at different facilities in Romania, and then we will initially deliver our experiment to Bremen in Zarm, at Zarm, where there we will first put all the experiments together. This part of interfacing with the others experiments and interfering is very, very important, because even if we think we do something right, that thing can influence in a bad way another experiment. So we will put every experiment together to test if everything works. Then also at some there will be some new tests that will also confirm that we are ready for launch. And then we will come back to Romania, and the organizers will deliver the experiments to Kiruna in northern Sweden. And in March 2022, there will be a 2-week long launch campaign that hopefully will end with a successful launch and recovery of the payload that all of our team members will attend to. And then that's also very, very important. We'll recover the samples. We will perform analysis on them in Romania, and then we'll share all the results. They will be open source to everyone interested. And also we will publish some scientific outputs. Yeah.
I think that is a great ending to this very interesting stream. A long path ahead, a lot that you have already learned, and a lot that you guys will for sure learn on the road to March 2022 while sending this rocket into space. Suborbital, not orbital, just to be clear. And you guys will surely learn a ton. And just as a reminder to all the people watching this, I hope that this has been an inspiration to all of you, because these kinds of students projects, it can be you. And the nice thing is that these guys have been working for a couple of years already and will keep working on this for another couple of years to actually launch hardware into space with the help, in this case, of the European Space Agency and others. And it just shows that if you really want to achieve your goals in space exploration, in this case, or in this case in 3D printing research, you can actually do that. And I really applaud you guys for that, and your whole team, of course, because you're even more than the two of you. I want to thank you for spending time with us and keeping on the Discord chat after this presentation and this stream ends. I would like to remind all the people that they can join the Discord server of Nexus Aurora by clicking the link below this YouTube stream. And I have been your host, Cohen, from the Next Astro YouTube channel. Thanks for your time, and we'll see you next week on Saturday, 4 p.m. UTC, at the next